Hello, I'm David Thibodeau. I'm the applications engineer for analog devices supporting the Sigma DSP products for the consumer group. And today, this video is going to be the first video talking about the ADAU1452, or what we call the Sigma 300. If you're totally new to this, you might want to watch one of my previous videos that was Intro to Sigma DSP and Sigma Studio to get more of the really basic overview. But I'm going to still start from a fairly basic starting point here. Um, yeah, so eval boards. What am I using? Well, of course, um, the evaluation boards are going to need. Every evaluation board comes with what's called a USB interface. And all this is you plug USB in on this side, and out here comes SPI and I squared C. So all this is a converter to convert to I squared C communications protocol or SPI communications protocol. And it is not meant to transfer audio. So it's only control programming the DSP and then controlling the objects in the DSP. So that's it. But it comes with every eval board, so you don't have to order this separately. And then I'll just quickly show you the old evaluation board. I'll put it on another camera here. And then I have what's called the revb. So let's put this under the other camera here and show that. And oops, get the cables out of the way. Too many cables. Anyways, this is the, let me see if I can make this readable. I think that's going to be legible. This is the 1452 Mini Z we call. This board is now obsolete. But there's a lot of them floating around, so you may actually have one and use it. It's not terribly different. It's still very usable. It has a few LEDs here for GPIO, which is kind of handy. A couple of the serial input ports are available on headers. Has a reset switch, has a self boot switch, and then of course the connection for the USB-I interface, the control port. This board only operates as SPI. Has a SPI EEPROM on it. And then the inputs are on the left and the outputs on the right. As you see, this is a double-sided board that the jacks and the op amps and such are on the bottom, which made this board a little more expensive to build. And there was a few features that really were a bit lacking. So we decided to obsolete it. So it is now obsolete. I'm doing my own sound effects. And enter the, oops, I was right the first time. The revb eval board. Ignore the part number here because this is we'll talk more about the Sigma 350. Technically, this is a 1466 that's on this board, but they're literally pin for pin compatible, and it makes no difference in what we're doing here. But you see, everything's on the top side on this one. So we've got the input jacks on the top. The output jacks, I'll warn you, are not in direct order. The first pair is the second one here. 0 and 1. We have some switches here for the self-boot function. It's on a little dip switch. And then some of the multifunction ports, the MP pins, 6, 7, and 8, have GPIO inputs for switches. There's only, over here there's a bank of LEDs, and we have one that shows power, one that shows if we're in self-boot, and then reset. And then there's a few LEDs that are on multifunction pins. Although the pins they're on are being used for LR clock for the codec. So it's limited usefulness, but I have used them. So then there's a couple of headers for two of the serial input ports. Serial output ports are either on test points or on holes where there are no test points stuffed. So they are available. There is a codec on board that has 4 ADCs and 8 DACs. So that's why we have 2 stereo inputs and 4 stereo outputs, because we're using this AD1938 codec. There is a reset button, And then the cool thing is there's a couple of the aux ADCs come up on pots. There's SPDIF in and out on optical connections, and then of course power comes in here. This board takes and then this is the SPI header. I mean the header for the USB-I, and so this is where you hook up the USB-I. But this board has a bit too much going on, so we don't power it up directly off of the USB port. We have to use an external power, and anywhere around 5 or 6 volts. It says here 7 volts max. There is a regulator. It regulates it down to 3.3. That's needed for the two parts. And then I believe the 5 volts is used for the op amps, if I were to check on that. Yeah, anything else to mention on this? No, I think we're good to go. So I'm going to plug this up, and oh, actually, first let me go over to the Sigma Studio screen, um, and let me see, because I want to show you when we I'm going to turn on this other camera too. Here, we'll turn on this other camera so you can see the eval board live. Um, yeah, so this is Sigma Studio. When you open up Sigma Studio, this is what you see, a blank project. And so what you do, I see spinning lights, spinning wheels. Okay, so what we're going to do is start a new project. This project I'm going to do today, we can talk about things along the way. It's a very simple project, and it's what I call the uh, input-output um, oscillator mute basic starter project. So basic input output meter oscillator, and it is a good file to store and put in a location on your computer, and when you want to do something, just call it up first, because it comes up with a lot of the simple a lot of the things you normally use already there. So kind of a bit of a shortcut. At least that's what I use it for. Um, and so, with that in mind, how do we start a project? Well, we go up here to the upper left and we select New Project. And then we drag in, we find a 1452 and drag it here. ADAU1452. We drag that into the project. It instantiates one object. You can drag in more than one, but that's a little more advanced for the moment. And below the palette of parts, you see communications channels, and the top one is the USB-I, or the USB interface. We got to drag one of those in, and you see it's orange. This is because, if you watch here, it's not plugged into the USB port. So I'm going to find the jack I have sitting here. There it is. It's hiding on me. Here's a USB port, and I'm going to plug it in, and as soon as I plug it in, you'll see it lights up, and then it turns green on Sigma Studio. So it says it sees the USB-I, and it is talking to it. Generally, this comes up as I squared C, the light. It's going to be a little hard for you to see that. But generally, the the I squared C light is on there. You can see it a little bit there. As soon as you try to compile, it'll switch over to the SPI as soon as it sees that SPI is what we're using. Most of our parts default to I squared C, and they can do both, so it's not a problem. What I usually like to do is then power up the eval board next. I'll just insert the power. You see things light up. Oh, I had a self-boot program in there that lit up a bunch of LEDs. So it might not necessarily look like this at the moment. And then you take the USB-I ribbon and you plug it in here, and you'll see another LED turn on when I do that. That LED right there turned on. Let me see, make sure you can see that. See, it's off. That's saying the USB-I power. There's 5 volts that is available in the USB-I for parts that are powered off of it, and we just bring that to an LED. It's a good indicator that it's alive and it's getting power, and you can use that in your projects and your hardware if you want to switch over or switch some of the communications. And so anyhow, I have audio coming from another computer here, channel 0 and 1. I'll plug that in there into the input. And then I have output here that's going into a little speaker, and I'll connect output 0 and 1 quickly. There's a little bit of hum there, to connect up the audio. So we're good. We have one more thing to do connection-wise, and that is actually to connect the USB-I to the 1452. Things to note is that on the bottom right of Sigma Studio, you see it says design mode. We're in a design mode. There's no program loaded. The basic functions of Sigma Studio is to compile a program and download it to the DSP. It does not run the program on the host computer. It runs it on the DSP. And then once its program is loaded, it's in what's like a runtime mode. And then all Sigma Studio does is talk to the DSP and control the objects or get information back like level, things like that, or memory locations, data that's in the DSP. And so those are the two basic modes of operation. So let's get moving and get the project rolling along here. Like I said, there's a lot of little topics to talk about along the way in this first video. So I go to the schematic tab. This DSP has the ability to do block processing too. Well, what is the difference? Well, the regular schematic main program, the way the Sigma DSP works, is for the most part, deterministic. It starts to run a program. It runs what you see visually on the screen every sample period, and then stops and waits for the next sample period. So it's sample-based processing, which is very much in tune with what happens with audio, for audio DSP programming. So new sample comes in, it picks it up, it runs the program, dumps the output, does all the math, dumps the output to the proper memory locations, and then waits for the next sample period. So that's how the core works. But we have a block processing for things like longer FFTs, etc., more block over like a 256 sample periods or something like that. But that's for a whole other discussion, because that's a lot more complicated. But we'll keep it simple. But in case you're wondering what these two tabs are, block schematic and regular schematic, that is because of that. So the main part is just sample-based processing. When we clicked there, the tree toolbox opened up. At least it should. If not, the icons are up here. There's two different kinds of toolboxes. This toolbox is not one I like as much. I prefer the tree toolbox. So if the second one here is not on, turn it on, because you can see what it looked like without it. It's so handy, I almost always leave it on. And then the capture window at the bottom should be on, because that's always handy to see. We'll talk about the output window later on. Yeah, moving along here. Let's start dragging in objects. I/O is a good place to start, input, output. This part has a lot of options. This is a digital only part, by the way. The only analog is the auxiliary ADC inputs, which is meant for like potentiometers or things like that. So we go to the input tab and we see we have 4 different input cells. I'll drag each one in here to show you, because it's the best way to see what the capability of the part is. Obviously, you can open up the data sheet and I expect you to memorize all 300 pages or whatever it is of the data sheet. That is a joke. Anyways, definitely reference the data sheet as much as you can, but it's a lot. There's a lot of information in there. So you see we have 4 serial input ports. We have 4 serial output ports on this DSP. They're independent of each other, so much so that you cannot slave from one to the other. So if you want to run the 2 serial ports, inputs and outputs from an external clock source, you have to jumper it external to the part. So keep that in mind. As you see, the first 2 serial ports, input 1 and 2, are capable of doing up to TDM16. So there's 16 different inputs on each one that's available. The last two serial ports only can go up to TDM8. Total, if you had two TDM16 data streams coming in and two TDM8 data streams, you would have 48 channels coming into the core. And then there's another way into the core with the sample rate converters, ASRCs, but we'll talk about that another time. And then, of course, the SPDIF, the digital audio input. So the Sony Philips digital interface. Um, anyhow, how these ports work. So this one is on a serial port, one serial port by itself. If you run I2S, which is stereo, you're going to get audio on 0 and 1, and you will not be able to get audio on any of these other channels because you just have it set for stereo, and that's it. You're getting two channels. If you set it for TDM4, then you're going to get input on the first 4 pins, and TDM8, the first 8 pins, etc., etc. So if you just have I2S coming in the case of the eval board, that's all we have. You have 2 channels on this one, 2 channels on that one, 2 channels on this one, and 2 channels on that one. So that is a limitation of the part. And we don't need these in the project right now. We're just going to use the first serial input port. Yep. I should also mention that the core, although I'm going to keep it simple as far as sample rates and stuff right now, but the core is its own object. It operates in its own clock domain. You can set it. Is a register settings, and then the serial ports operate in their own clock domains, and they just communicate by putting data into memory locations. So the serial port comes in, puts its data into memory, and then the DSP core picks it up from that memory, processes it, and dumps it in another memory location. And then the serial output port picks up the data from that memory location and outputs it. And so you have to get all these settings correctly sample rate wise. Otherwise, you might miss samples, you might skip samples, you might add, you might have duplicate samples, that sort of thing. So, but that's another larger discussion because it goes more into clocking and such. This part is quite a complex part. And yeah, what else do I need to quickly go into? Oh, I should probably quickly show the hardware configuration because we were in the hardware. I'm going to go back to this hardware tab where we set up the part. We set up the communications. There's a sub tab down here called register controls. You click this open and you have the registers of the part. There's a lot of sub tabs along the top. So clock, core, we got the routing matrix, the serial ports, serial port setups. So there's a lot here, a lot of registers, but it's all nicely done. Yep, so back to the schematic. We're gonna pick up, what do we want to do? I want to be able to switch between, well, let's just get audio going first and make sure everything's working. So let's get a volume control because I really need a volume control. Let me collapse this I/O. Volume control. Oh, adjustable gain. We're gonna, let's take the hardware slew. Single volume, hardware slew. So there we go. Now, this is one channel. As you see, there's one in, one out. So I'm going to go on the bottom part. You see where the hand changes? And right click and grow this algorithm by one more input to make it 2 inputs. So now it's stereo. If you right click, you see it changes the hand. If you right click up here on the scale, you get the setting of the pot. You can adjust the range, max and mins, and the step size. The step size is only to prevent lots of communications going out and overwhelming the part with inputs, with especially if it's I2C, because it's slower communications. But SPI, it's a little bit more, but you end up with a lot of data being sent in the part. So that just helps, yeah, just like I said, to not crowd the communications when you just pull the slider up and down on the GUI, it's not going to send 300,000 messages. Uh, it'll just do every couple of dB. And with the hardware slew, it's going to slew between them, so it works really great. Oh wait, let's make the connection. Sorry if I'm talking too much. um, there's a lot to say. I have a lot to say. So do that. I always recommend putting in some meters so we can see what's going on. Level detectors and lookup tables. So level detectors, single band. We're going to take this, my favorite one, the one with a numerical display, single level. This you cannot grow. So what you can do is Command copy, Command V, and we end up pasting in another copy. I could drag another one in from the library, and there's another trick with the control key, but I'll talk about another time. Let's hook that up. And it's always another thing I always like to do. Well, no, let's just get output. Let's just get output, and we'll add more later. Okay, those are the input cells. Let's go to the output cells. The output cells are configured a little differently. The serial ports are configured the same as inputs, where there's serial port 0 are the first 16 outputs of the core, and then 16 through 31 is the second serial port. And so what they do, I mean, you can grow this if you want to. I usually keep it separate cells because a lot of times they're in different places in the project, so it's good to have them separated out. But here you can select what channels out of the 48. So you go from 0 to 47. Although I'm fine, 0 is what we want. So let me do the control trick. I'm going to hold the control key down, click and drag and let go, and you make a copy. And so we have 0, output 0 and 1, which is what I want in this case. It's the first serial port, and away hook those up, and I should be able to link compile download. Way up here, link compile download. Here's where we're going to actually program the DSP. If you look on the bottom, it still says design mode, bottom right. Still says design mode. So I'm going to go back up here, link compile download, does its work, and then on the bottom right you see active downloaded. So now I should be able to play the music on this other computer, and we can hear it. Voila. And we should have volume control. Look at that. And then we should be able to see it in the meter. It's a noisy source. Actually, it's my other computer's noise. There's probably a ground loop between them. Anyways, yeah, so that's, it's working. It's awesome. It's working. So things I always like to add to a project, which should be in this project, are first off, I guess I'm going to say this. This is more for a good troubleshooting and a good test. So go to the sources on the library and DC input entry. The one that says no MIPS is not really very usable. It's just pretty much a constant. It's rare when that is handy, but it's there. It was there for a specific reason, but I really basically never use it. So drop in a DC cell. All this is it puts a number in, which means DC. It's a great place to have a constant. If you need constants in your program, you use a DC cell. So, okay, so we did that. Then let's go to the basic DSP functions. In here we have DSP readback. Drag that in and connect these two. What this is going to do is the DC cell resides in the DSP program. The readback is a function in Sigma Studio that goes to the DSP, gets the data from a specific memory location, reads it back and displays it. So if you're not sure if you're actually communicating with the DSP, then this is what you do. Put these two cells in and see if you got communications. That's step number one. Now note, since we dropped in some new objects, this changed back to design mode on the bottom right. So right now it's not working. Although the DSP program is still running, I can still play audio. So anyways, but I can't control it. I don't think it's gonna control. See, no control because it's in design mode. So let's link compile download and keep this running in a loop. So link compile download. Now I have control. I'll have control. Beautiful. Okay, so now it has number 1 in here. I'm gonna hit read and it should read a 1. So we have communications. I can come in here and change this to a 2. So I changed it to a 2 in the DSP, and I can read it back to see if it actually changed to a 2, and it did. So this is a really good troubleshooting tool. I recommend it all the time, especially if you're using SPI, because with SPI, you don't know, the DSP has there's no handshaking. So it just downloads and trusts that the DSP got it, which isn't always true. So check that first. That you're actually communicating with the part. The other thing to note is, let me go back to the register tabs. This is an important little detail. There's a read all registers. If you go back to the 1970s, or 60s, danger, danger, Will Robinson. Do not click that unless you have saved your project. Because if the SPI communications is not working, all you're going to get back is FFFFF or 0000. I think it's usually FF, but one or the other. And it will set every register to FFFFF in Sigma Studio. So the memory in here for all these register settings is, you have the data, all these settings, all the settings will change and cross the entire thing, and it's going to make a mess. So with a part with this many registers, don't do read all registers. It's better off to use the DC cell and the readback, get the communications going, then you trust it. And if you're ever going to use that read all, which is very rare, I would recommend you make sure your project's saved first and then call it back. There is no auto save, by the way. So, all right, enough on that. Go back to the project. I don't want this video to get too long. So what are the other things I usually do for basic things? Well, I like to have some mutes because a lot of times you need to check. I use the no slew types. Okay, so I went to volume controls, mute, no slew, and just the regular mute, not the multiple control one. And I just drop these in to the path here, and don't forget to connect it. You can click on a wire and grab the endpoint and just move it over. You don't have to rerun it, which is handy if it's coming from a long way. So I like to have the mutes here because to make sure left is left, right is right, to make sure the right channels are in the correct place in TDM mode, that you're picking them up correctly, that the upper 4, lower 4 aren't swapped on a TDM 8 or anything like that. So it's very handy for confirmation that something's working and the right things are in the right place. The other thing I like to do is add an oscillator source. Because I don't always have input, it might be a bit of a pain in the neck to get input from somewhere else, but I want to test things in a project. So use an oscillator. We have the ability to create a signal source in the DSP. So go back to sources. I can collapse this DC one. And you see one category of oscillators, of which there are a number of different oscillators, and sine tone is usually what you're going to use. We pull that in, and boom, you have a mono oscillator. Now this oscillator is a little bit more advanced than the one we had in the 1701, the ADAU1452. You have a phase control, which is interesting, if you have more than one. And we have a dB, so you can set the output directly in here, which is fine. If you're getting low on MIPS, you can do that. I still like to have a volume control. So I'm just going to copy this one, and I'll show you another thing about reduce. I said copy, not drag. Control key, click. There we go. That time it worked. Um, Now I only need one input because there's only one output. So I'm going to right click on this and reduce the algorithm. Of course, it only lets me reduce it to 1. I only grew it by 1. So you can add or reduce. You don't have to throw it away. But, okay, no buts here. Hold on. No but yet. Let's get a switch going on because we need a switch between these two. That is under the muxes and demuxes because a switch is a multiplexer. So we go under multiplexers, and now it started to be called a switch in the library. And I'll use the no slew. Slew is where it will crossfade between the selections. As you switch it, it will crossfade and make a smooth transition. For a test project, I don't necessarily need that. Or if it's something that's not changed often in your project, there's no need to use the MIPS for doing a slew. Um, so kind of your call on your application. Um, and sometimes it's okay to if there's a little click or something because nothing's going on at that time. But if it's something that's actively changed, you'd want to use a slew. We're going to do 2 channels because we're stereo. So we'll bring the stereo switch in here. And let's hook up the inputs into the top 2. So that when this radio button is on, these top 2 are active and are being sent out to the outputs here. So we'll connect the outputs to the volume control. So these bottom 2 are when the bottom radio button is selected. And so we have this one output needs to go to 2 places. We could pull up a mixer or a splitter. There's plenty of splitters, but that uses MIPS. We don't really need much control here. All we need to do is just Y it, get a Y chord. So that's called a T connection. So we pull up the T connection, and what's good about this T connection is it's free. It does not use any MIPS. It's just a memory location that it tells this cell pick up the data from this memory location, and that one pick it up from the same memory location. It's simple as that. The compiler takes care of all that for you. So it's a free way to Y a signal. In case you're wondering about why. Okay, another pun. Yeah, we're good. Let's compile downloads this. Oh, the reason why, by the way, I like the oscillator because it's just more user friendly. I like to see instead of looking there, does it say minus 30, minus 20? But it's just me. I like this slider interface, and I recommend you bring the oscillator down a good 25 to 30 dB because these oscillator objects are at full scale, 0 dBs full scale for the 24-bit serial port in and out. And let's link compile download. And I should be able to go to the oscillator, and voila, you should hear that. And I can bring it up and down. Woo, and you hear the zipper noise. Because this one's not a slew. And of course you can shut it off. We're on. So anyways, this is the basic project. How far along am I on the video here? 33 minutes. Yeah, I should probably stop here with one exception though, and that's the output window. I should show that and then we call it quits here. Output window. This is where when you link compile download, it will store the information. It will show you the information on the compilation, which is very handy. It tells you the part it used, the 1452, 5X assembler, but it will assume it has the sampling rate setting here of 48K. It'll show you the level meters, the input output, readbacks, DC, all this stuff, how many MIPS, how many instructions they use, how many cycles it uses, because sometimes there's loops, and then how much memory, DM0, 1, and program memory, give you totals, and then a percentage of usage. This first column, instruction cycles, it's usually what you need. So that's using 3%. So we're we're really pushing this DSP at the moment. Yeah, so we're using 3% of the power that's available of the number of instructions that are available, or what I always refer to as the MIPS. Um, uh, yeah, the the difference between the 1450, the 1451, and the 1452 is the system clock rates and the amount of memory available. The system clock rate on the 1450 is half, so it has half the number of cycles or MIPS. And so, but the cores are exactly the same, so the programs will run. Um, but if you have more than 50% of usage on a 1452, that program won't run on a 1450 because it has too many MIPS. Likewise, if you're using more memory for delay than the 14 and the 1452, then that the 1451 would work. So, okay, let me say that a different way. If you're using a lot of delay memory in a 1452, and you try to run that program in a 1451 that has less memory, you're going to have an issue. It's going to fail, or it's not going to work. Um, so keep that in mind that these cores are the same. When you go to the Sigma 350 family, um, it's the same thing. It's the same core. So the programs will work. But now it depends on other peripherals that might be slightly different. Depends on what you're using. So from a 1452, 50, or 51 program, you can go to a 1456, etc. That family, the Sigma 350 family, and with no changes. Just port it over, run it. It works fine, um, and that's it. But if you go downwards, if you go backwards, then you have to really look at memory usage, what pins are using, ports, and that sort of thing, because there might be some differences, and obviously it won't work. Um, so, uh, so yeah, that's the basics. Thank you for listening, and tune in for the next video.